Right now, you're placing your hand on the table and the table is holding you up. But here's the truth. Your hand never actually touches the table. 99.9% of atoms is empty space. If you inflated an atom to the size of a football stadium, the nucleus would be a single pea standing alone on the field, and the electrons would be flies buzzing in the upper rows. And the distance between your hand and the table, on a galactic scale, is a vast, endless abyss. But wait, this is only the beginning. Because even that empty space isn't truly empty. According to quantum mechanics, it's filled with a constantly churning swarm of virtual particles that pop in and out of existence. We call it quantum foam. The universe, even at the smallest scale, is never a still, silent nothingness, but a wildly active sea of energy. And you never felt it because your intuitions didn't evolve to perceive a reality like this. Let's pause here and think about what this really means. When you look at your hand, you see solid flesh, skin, bone. It feels real. It feels sturdy. But zoom in with the most powerful microscope imaginable, past cells, past molecules, past the atoms themselves. And what do you find? Almost nothing. An atom's nucleus is so tiny compared to the electron cloud that if the nucleus were a marble, the nearest electron would be half a mile away. And in between? Nothing but probability waves, quantum fields, nothing but mathematical abstractions somehow made real. This is the universe you live in. This is what you're made of. Not solid matter, but clouds of probability, fields of potential, mathematical patterns dancing in emptiness. So why don't you fall through the floor? Because when your electrons approach the table's electrons, quantum mechanics' Pauli Exclusion Principle kicks in. Two electrons cannot be in the same quantum state. When Wolfgang Pauli proposed this principle in 1925, no one understood how radical it was. It wasn't just a technical detail about particle physics. It was a fundamental law that makes chemistry possible, that makes solid matter possible, that makes you possible. And even stranger, an electromagnetic force rises between these electrons. But you can't explain it with a familiar mechanical analogy like a rubber band. Electromagnetism is a fundamental property of the universe, a bedrock truth, and it's where explanations end. Richard Feynman said exactly this in his Nobel lecture. Why do magnets repel each other? I can't explain it to you with springs or mechanical parts, because electromagnetism is the very thing that already explains those mechanical parts themselves. At some point, you have to accept that the universe is just that way. And here, the deep honesty that science offers you emerges. Science isn't telling you a comforting fairy tale. It isn't pretending there's as if there were a spring force. But that spring is actually a dance of quantum fields, virtual photons. Yes, even particles of light are the carriers of this repulsive force. And Heisenberg's uncertainty principle. The uncertainty principle says you cannot know both the exact position and exact momentum of a particle simultaneously. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of our measuring tools. It's a fundamental feature of reality. Particles don't have exact positions and momenta at the same time. They exist in clouds of probability until you measure them. And those virtual photons? They're popping in and out of existence constantly, borrowing energy from the vacuum for brief moments before disappearing again. They're allowed to do this because of the uncertainty principle. As long as they disappear quickly enough, they don't violate energy conservation. The vacuum isn't empty. It's seething with activity, a quantum ocean of possibility. Now let's go deeper. As your hand and the table repel each other with an infinite number of quantum interactions without ever making contact, you only feel solidity. But what you call solidity is actually the macroscopic result of negative electron clouds repelling each other. And that repulsion is so strong that you can't push the table's atoms through your hand's atoms. The energy required is on the order of the energy in a hydrogen bomb explosion. Think about it. The act of touching something that you do every day is, at the quantum level, a tremendous electromagnetic war. Billions upon billions of electrons, each one surrounded by its electric field, each one obeying the Pauli Exclusion Principle, each one exchanging virtual photons with every other electron nearby. It's a dance of unimaginable complexity, and yet your brain reduces it to a single sensation: solid. And you perceive it as a light touch, because your evolutionary intuitions were shaped to survive on the Serengeti, not to understand the quantum realm. Your ancestors' brains evolved to calculate whether a lion's claw would tear their skin, not to evaluate quantum tunneling probabilities. They needed to know if a branch would support their weight, if a stone was sharp enough to cut, if the ground was stable enough to run on. They didn't need to know about electron orbitals or electromagnetic field theory. And this isn't your fault. It's nobody's fault. But it means you can't understand the universe by trusting your everyday intuitions. Einstein knew this very well. He said, "Common sense is nothing more than a collection of prejudices acquired by age 18. And science does exactly that. It shatters your common sense, destroys your prejudices, and shows you the universe as it is. Strange, mathematical, counterintuitive, yet woven with a deep consistency. Consider what science has taught us about the nature of reality. Time is not absolute. It flows at different rates depending on your speed and proximity to massive objects. Space is not a fixed stage on which events unfold. It can bend, stretch, ripple like a fabric. Matter and energy are interchangeable, related by that famous equation E equals mc squared. Particles can be in two places at once. The act of observing something changes what you're observing. Cause and effect can become muddled at the quantum level. None of this makes intuitive sense. All of it is true. And here, the grandeur of science's 400-year avalanche-growing adventure of discovery appears. When Isaac Newton published Principia Mathematica in 1687, for the first time in human history, he proved that the sky and the earth are subject to the same laws. The moon is falling, just like an apple. It just misses the earth because it's moving fast enough. And this was a revolution that shattered the cosmic hierarchy in people's heads up to that point, eliminating the artificial distinction between the celestial and the terrestrial. For thousands of years, humans had believed the heavens operated by different rules than the earth. The stars and planets moved in perfect circles because they were made of a different, purer substance. The earth was corrupt, changeable, imperfect. But the heavens were eternal and unchanging. This wasn't just science, it was theology, philosophy, the foundation of how people understood their place in the cosmos. Newton destroyed that comfortable hierarchy with mathematics. He showed that the same force that pulls an apple to the ground pulls the moon toward the earth toward the sun toward the galactic center. Gravity is universal. The laws of motion are universal. There is no distinction between celestial and terrestrial. We are all part of the same cosmic dance. Newton's law of gravity was not just a formula. It was proof that the universe, everywhere, always, speaks the same mathematical language. Then, in 1676, Euler Roemer, by observing the eclipses of Jupiter's moon Io, discovered that light has a finite speed. When Earth was closer to Jupiter, the eclipses were early. When it was farther, they were delayed. And this delay was proof that light needs time to travel through space. The speed of light, 299,792,458 meters per second. But this isn't just a number. It is a universal conversion factor where space and time transform into one another, as Einstein showed us with the special theory of relativity in 1905. Einstein realized that the speed of light is the same for all observers, regardless of their motion. This seems impossible. If you're running toward a beam of light, shouldn't you measure it moving faster than if you're running away? But no, light always moves at exactly the same speed, no matter what you do. The only way this can be true is if space and time themselves adjust to keep the speed of light constant. Moving clocks tick slower. Moving objects shrink in length. Simultaneity, the idea that two events happen at the same time, becomes relative depending on the observer. And then Einstein went further. In 1915, he published his general theory of relativity, which showed that gravity isn't a force at all. It's the curvature of space-time caused by mass and energy. The sun doesn't pull on the Earth. The sun warps space-time around it, and the Earth follows the curved path through that warped space-time. We call it falling toward the sun, but really we're taking the straightest possible path through curved space-time. This sounds abstract, but it's been confirmed countless times. GPS satellites have to account for relativistic effects, or they'd be off by miles. We've detected gravitational waves, ripples in space-time itself, caused by colliding black holes billions of light years away. We've photographed the shadow of a black hole, where space-time is curved so intensely that not even light can escape. When Maxwell discovered in the 1860s that electricity and magnetism are actually two faces of the same force, and that light is an electromagnetic wave, different branches of physics began to merge. Optics, electricity, magnetism, all united in Maxwell's four elegant equations. Before Maxwell, these were separate phenomena. Electricity was lightning and static shocks. Magnetism was compass needles and lodestones. Light was something else entirely, perhaps tiny particles shot from luminous objects, perhaps waves in some mysterious medium. Maxwell showed they're all aspects of the electromagnetic field, a fundamental entity that permeates all of space. And he proved that light is an electromagnetic wave, oscillating electric and magnetic fields propagating through space at, you guessed it, the speed of light. Not approximately the speed of light. Exactly the speed of light, predicted by the theory with perfect precision. This wasn't a coincidence. Light is electromagnetic radiation. In a narrow band of frequencies your eyes happen to detect. Then the 20th century came and everything got even stranger. Planck started quantum physics by solving the blackbody radiation problem, introducing the radical idea that energy comes in discrete chunks, quanta. Einstein discovered photons, showing that light itself is quantized, sometimes behaving like a wave, sometimes like a particle. Bohr developed the atomic model with electrons in specific orbits, explaining why atoms emit light at particular wavelengths. Heisenberg revealed the uncertainty principle, showing that the act of measurement fundamentally disturbs what you're measuring. Schrödinger wrote the wave equation, describing particles as probability waves that spread through space. Dirac predicted antimatter, and within a few years it was discovered. Particles with the same mass as ordinary particles, but opposite charge. And each is a moment of understanding rising on the shoulders of the other. Planck's quantum, Einstein's photon, Bohr's atom, Heisenberg's uncertainty, Schrödinger's wave, Dirac's antimatter. Each one seemed bizarre when first proposed. Each one was confirmed by experiment. Each one opened new questions, new mysteries, new frontiers. And each is a moment of understanding rising on the shoulders of the other. Planck's quantum, Einstein's photon, Bohr's atom, Heisenberg's uncertainty, Schrödinger's wave, Dirac's antimatter. Each one seemed bizarre when first proposed. Each one was confirmed by experiment. Each one opened new questions, new mysteries, new frontiers. But now, let's come to the truly shocking question. Why is it like this? Why is there the Pauli Exclusion Principle? Why is there the electromagnetic force? Why does quantum mechanics work this way? And here is the most honest, most unsettling answer science can give you. We don't know. And maybe we will never know. Because at some point, you reach bedrock truths. A point where the universe is just this way, and there is no deeper explanation. Feynman explained it like this. You can explain to a 5-year-old why a toy works. It has springs and gears inside. But if that child asks you, okay, but why do springs work like this? You talk about electromagnetic forces. If they ask, then why do electromagnetic forces exist? You stop there. Because that is the boundary of what we know. And this is not an inadequacy. It is honesty. Science does not claim it will explain everything. But everything it can explain it presents with mathematical precision, in a way that is testable by experiment and verifiable again and again. The universe never owed you a comforting story of why it's like this. It simply is. It works with mathematical laws. And we humans are the species that, by accepting this strangeness and taking not our intuitions, but our reason and mathematics as our guide, has managed to unravel the mysterious fabric of reality. Some call this unsatisfying. They want a reason, a purpose, a why beyond the how. But perhaps that's asking the wrong question. Perhaps the universe doesn't need a reason to be the way it is. Perhaps existence itself is the ultimate brute fact, and everything else follows from the laws we've discovered. Or perhaps there are deeper layers we haven't found yet. Perhaps string theory will succeed in unifying all the forces, showing that electromagnetism, the weak force, the strong force, and gravity are all aspects of vibrating strings in higher dimensional space. Perhaps we'll find that the constants of nature, the speed of light, the strength of gravity, the charge of the electron, are determined by some deeper principle we haven't discovered. Perhaps we'll never know. But this is the adventure of science. Not knowing is not failure. Not knowing is the frontier. And now, let's look at an even bigger perspective. Where did the atoms in your body come from? Every atom was cooked in the hearts of stars billions of years ago. Light elements in fusion reactions, heavy elements in supernova explosions, and then scattered across space, eventually gathered in a gas cloud. The solar system formed, Earth took shape, and those atoms, after a 4.5 billion year journey, came together in your body right now. As Carl Sagan said, we are star stuff, a way for the universe to know itself. But this isn't just a poetic expression. It is literally a scientific fact. Your calcium was created in the death of a star, your iron in a supernova, your carbon in the core of a red giant. The hydrogen in your body, the most common element in your cells, was forged in the first 3 minutes after the Big Bang, when the universe was a hot, dense plasma of quarks and gluons, cooling just enough for protons and neutrons to form. Think about the journey of a single carbon atom in your body. 14 billion years ago, it didn't exist. The universe was too hot for atoms. Then, as the universe expanded and cooled, quarks combined into protons and neutrons. Protons became hydrogen nuclei. For hundreds of millions of years, the universe was dark, filled with hydrogen gas, slowly cooling, slowly clumping under gravity. Then the first stars ignited. Massive stars, hundreds of times the mass of our Sun, burning hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. And when those stars ran out of fuel, they exploded in supernovae, seeding space with the heavy elements they'd created. Your carbon atom was born in one of those explosions. It drifted through space for eons, part of a nebula, a cloud of gas and dust. Eventually, that cloud collapsed to form the solar system. Some of the material became the sun, some became planets, and some became the Earth. Part of your DNA, perhaps, part of a protein in your muscles, part of the glucose fueling your brain as you process these words. And now, those atoms have come together in your hand to press on a table. But they don't touch because quantum mechanics keeps them apart. Think about it. You are a temporary arrangement of atoms born from a star's death. And these atoms never truly touch each other. They are held together by electromagnetic forces. And you, within this temporary arrangement, are consciousness. You can think. You can understand the universe. Isn't this one of the most extraordinary ways for the universe to understand itself? Now let's return to your daily life and look at the other ordinary miracles science shows you. You see a tree. But where did that tree come from? Most people say, from the soil. Wrong. 95% of a tree's mass comes from the air, from carbon dioxide and water. Photosynthesis uses sunlight to turn atmospheric CO2 and the water it takes from its roots into glucose. So the tree literally turns air into solidified sunlight. The atoms in the tree's wood came primarily from the air you breathe. The soil provides minerals, nitrogen, phosphorus, potassium. But the bulk of the tree, the carbon that makes up its structure, came from carbon dioxide molecules floating invisibly around you. And now when you burn that tree, you see fire. But what is fire? Fire is the release of the solar energy that tree stored for years, released back in a rapid reaction with oxygen. Flames, energy released from the breaking of atomic bonds, heat and light. Every fire is a delayed echo of the nuclear fusion reactions that happened on the sun's surface millions of years ago. The warmth you feel when you bring your hand close to the fire is infrared photons striking your skin and vibrating your molecules. And your nerve cells convert that vibration into electrical signals and send them to your brain. And the brain interprets it as heat. But heat is not out there. It is inside you. Out there are only fast-moving molecules. Temperature is just the average kinetic energy of molecules. When you touch something hot, fast-moving molecules in that object collide with molecules in your skin, transferring energy, making your molecules move faster. Your nerves detect this increased molecular motion, and your brain creates the sensation of heat. Cold is the same. There is no such thing as cold, only molecules moving more slowly. At 0 Kelvin, negative 273.15 degrees Celsius, in theory, all molecular motion stops. But quantum mechanics leaves a zero-point energy even there, because Heisenberg's uncertainty principle does not allow a particle to be both completely motionless and in an exact position. Even at absolute zero, the coldest possible temperature, quantum uncertainty keeps particles jiggling. The universe won't let anything be perfectly still. The problem of consciousness may be the hardest, deepest question in science. And maybe it points to another bedrock truth, a point where explanations stop. Or maybe we'll solve it. Maybe consciousness is an emergent property of sufficiently complex information processing. Maybe it's quantum effects in microtubules in neurons, as some have speculated. Maybe it's something we haven't imagined yet. We don't know. And that's okay. That's where the frontier is. And look at colors. Every color you see around you is electromagnetic radiation at a certain wavelength. Red, about 700 nanometers. Violet, about 400 nanometers. But the universe shows you only this narrow window. The electromagnetic spectrum is vast. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. And you can see only 0.0035% of this spectrum. Your eyes evolved to become sensitive to the wavelengths of light the sun emits most intensely, because that provided the most useful information for survival. But a bee can see ultraviolet beneath visible light. Flowers that look plain white to you are covered in intricate patterns visible only in ultraviolet, guiding bees to nectar. A snake can see infrared, detecting the heat signature of prey in total darkness. And for them, what we call color is completely different from yours. Color is not out there. It is inside your brain. Out there are only electromagnetic waves vibrating at different frequencies, and your brain categorizes them as red, blue, green. This is what we call qualia, subjective experience. The redness of red, the painfulness of pain, the particular way it feels to be you, experiencing the world from your unique perspective. And science still cannot explain exactly how qualia arises. We can map every neuron in your brain. We can track every electrical signal. We can watch which regions light up when you see red or taste chocolate or hear music. But we cannot explain why there is something it is like to have those neural patterns. Why consciousness feels like something from the inside. Now look at your hand again. That emptiness, that push, that feeling. None of it is an illusion. But it is also not what you think. It is a superficial reflection of the deepest truth of the universe. And you live it every day, every second, without noticing. When you move your hand, Billions of neurons fire in coordinated patterns, sending electrical signals. Muscle fibers contract, and that contraction also occurs thanks to electromagnetic forces. Actin and myosin filaments pull on each other, but again, they never truly touch. Every movement, every breath, every heartbeat is a manifestation of quantum mechanics, electromagnetism, thermodynamics, and you do it without thinking because evolution automated it for you. But now, thanks to science, the curtains are pulled back, and the incredible machine of reality appears before your eyes. This is a human triumph. Over 400 years, with telescopes, microscopes, particle accelerators, spacecraft, mathematical theories, experiments, we humans have managed to solve the deepest secrets of the universe. We have measured the age of the universe, 13.8 billion years. We have detected the cosmic microwave background, the afterglow of the Big Bang itself. We have discovered planets orbiting distant stars, thousands of them, and some might harbor life. We have photographed galaxies billions of light years away, seeing them as they were when the universe was young. We have split the atom and harnessed nuclear energy. We have sent robots to Mars and probes to the edge of the solar system. We have built machines that can think after a fashion, artificial intelligences that can recognize faces, translate languages, even generate text and images. We have sequenced the human genome, 3 billion base pairs of DNA, the instruction manual for building a human being. And this journey isn't over. Dark matter, dark energy, quantum gravity, consciousness. There are still mysteries waiting to be solved. Dark matter makes up 85% of the matter in the universe, yet we've never directly detected it. We know it's there because of its gravitational effects. Galaxies rotate too fast. Galaxy clusters hold together too strongly without it. But we don't know what it is. Exotic particles? Modified gravity? Something stranger? Dark energy is even more mysterious. It makes up 68% of the universe's total energy, and it's causing the expansion of the universe to accelerate. Galaxies are moving apart faster and faster, driven by this unknown force. In the far future, trillions of years from now, if dark energy continues, every galaxy outside our local group will recede beyond the cosmic horizon, forever beyond reach. The night sky will go dark. Quantum gravity is the holy grail of physics, a theory that unifies quantum mechanics and general relativity. We have two extraordinarily successful theories, each tested to incredible precision in their own domains. But they contradict each other. Relativity says space-time is smooth and continuous. Quantum mechanics says everything is discrete and probabilistic. At the Planck scale, the smallest possible scale of distance and time, both affects matter, and we don't know how to combine them. String theory, loop quantum gravity. These are attempts to solve the problem, but neither has made testable predictions yet. We're still searching. And consciousness. How does subjective experience arise from physical processes? Is it unique to biological brains, or could a sufficiently advanced computer be conscious? Could an AI truly understand, or only simulate understanding? We don't know, but every discovery is built on the previous one. Newton built on Galileo. Einstein built on Maxwell. Quantum mechanics built on centuries of chemistry and physics. And maybe one day, maybe your generation or your children's generation will solve these final secrets too. Or maybe find new, deeper questions. Because science never ends. It only deepens. Every answer reveals new questions. Every mystery solved opens new frontiers. The more we learn, the more we realize how much we don't know. And that's not a failure. That's the glory of it. The universe is larger, stranger, more intricate than we imagined. And we get to explore it. And you, right now, are part of this immense cosmic adventure, born from stardust, held together by quantum fields, conscious, thinking, understanding. You are atoms that can contemplate atoms. You are the universe looking back at itself, asking questions, seeking answers, marveling at its own existence. Does that feel small to you? Because it shouldn't. You are one of the most beautiful examples of the universe's attempt to know itself. And that may be a more miraculous truth than anything else.